Welcome to Unit 17, video number 3. This video will focus on acid and base strength. By the end of this video, you should be able to differentiate between strong and weak acids and strong and weak bases in terms of dissociation. You should be able to relate acid and base strength to equilibrium position. And you should be able to explain how the strengths of conjugate acids and bases are related. As you probably remember from the acid strength activity we did in class, the biggest difference between a strong acid and a weak acid is the degree of dissociation, or how much of the acid dissociates when put in water. So let's compare a strong and a weak acid. We'll start with a strong acid. The strong acid here is represented by HA, which is any one particular acid. It could be any strong acid, like HCl or HNO3. So let's say I put 50 molecules of HA in water, and I'm making these numbers up. Every single one of those HA molecules will dissociate to give us 50 H pluses and 50 A minuses, and leaving us with 0 undissociated HA molecules. This strong acid has 100% dissociated, or 100% ionized. Turning, however, to the weak acid, if we do the same thing and put 50 weak HAs in water, only say maybe 2 will dissociate, giving us 2 H pluses and 2 A minuses, and leaving us with 48 undissociated HA molecules. This weak acid has dissociated very little. In fact, most weak acids dissociate less than 1%. So in summary, the biggest difference between a strong acid and a weak acid is the degree of dissociation. Strong acids dissociate completely, weak acids do not. So let's take a look here at a more specific example of a strong acid. In this case, our strong acid is HCl, and it completely dissociates to form Cl- and H3O+, which remember is just a water molecule with an H+ ion attached to it. Because it completely dissociates and puts a whole lot of ions in solution, it's a strong electrolyte. It would light our light bulb very brightly. We also see that the reaction goes to completion. It does not establish an equilibrium. This is signified by the one-way yields arrow. Looking at an example of a weak acid, on the other hand, in this case we have CH3COOH, or if you prefer, HC2H3O2. These are the same thing. They're both acetic acid. This weak acid will dissociate to a much smaller extent, forming only some H3O+ ions and some CH3COO- ions, or C2H3O2 ions if you prefer the other notation. This makes it a weak electrolyte because it puts fewer ions in solution. It also means that it establishes an equilibrium, as we can see by the double-sided arrow. This means that the reverse reaction is also occurring. While we generally focus on acid strength, base strength is also important to understand. We define strong bases as substances with strong affinities for H+. Because they also put a lot of ions in solution, they're strong electrolytes, and they also go to completion. These reactions go to completion, again, as you can see by the single-sided yields arrow. So take, for example, the strong base O2-. O2- has an incredibly strong attraction for one of the H+ ions in water. If we rewrite water HOH, we can see that the O2- ion will come in, grab an H+ from water, and form an OH- ion. It will also leave behind the OH- ion from the water that's been stripped of its other H+, giving us 2 OH- ions. A weak base, on the other hand, has a much weaker affinity for H+ ions. making it a weak electrolyte. And it also, like a weak acid, establishes an equilibrium, as indicated by the double-sided equilibrium arrow. In this example, the weak acid CO3 is not able to attract all that many H pluses to itself. Only some of these molecules will grab an H plus to form HCO3- and OH-. So let's put the pieces together and see how acid and base strength fit in with the Bronsted-Lowry definition of acids and bases. I'm going to start down here with this strong acid example. So take HCl, the strong acid. HCl has a greatly favored forward reaction. As we said, nearly 100% of the HCl will dissociate to form Cl- and H3O+. This means that its conjugate base, Cl- will not be able to cause any reverse reaction to occur. It will not be able to attract an H plus from H3O+ to form H2O and HCl. This means that Cl- is a very weak conjugate base. So generally, strong acids have weak conjugate bases. Turning our attention to the weak acid example at the top, our weak acid, HCO3-, is not able to dissociate 100%. In fact, the forward reaction does not occur to a great extent. At equilibrium, there are far more reactants than there are products. The equilibrium position lies towards the reactants. This means that the conjugate base of HCO3- or CO3 is able to pull some H pluses away from H3O+ and form H2O and HCO3-. The reverse reaction does occur to quite a large extent. This means that the conjugate base is strong. So in summary, as acid strength increases, the strength of the conjugate base decreases. Likewise, as acid strength decreases, the strength of the conjugate base increases. Here's a list of some very common strong acids and weak acids and strong bases and weak bases. Take a look at the strong acids at the top. Notice that each of their conjugate bases, which I'm writing next to them right now, are exceptionally weak conjugate bases. They're not strong enough to pull any of the H pluses off of the H3O+ and cause the reverse reaction to occur. Therefore, these reactions go to completion. These weak acids down here, however, have much stronger conjugate bases. These conjugate bases are able to grab onto an H plus and cause the reverse reaction to occur to at least some extent. So again, as the acid strength increases, the conjugate base strength decreases. That brings us to the end of this video. Let's quickly review our goals. First, we learned how to differentiate between strong and weak acids and strong and weak bases in terms of dissociation. We said that strong acids dissociate 100% in water, and weak acids dissociate generally less than 1% in water. We also differentiated between strong and weak bases in terms of affinity for H plus ions. Remember, strong bases have a high affinity for H plus, and weak bases have a low affinity for H plus. We also related acid and base strength to equilibrium position in a Bronsted-Lowry acid-base system. And we talked about the strengths of conjugate acids and bases. Recall that as acid strength increases, conjugate base strength decreases. And as acid strength decreases, obviously conjugate base strength increases.